The discovery of K2-12B, a new era in the search for life. As you gaze into the night sky, your eyes tracing the countless stars, distant galaxies, and vast mysteries scattered across the universe, one profound question quietly lingers in the back of your mind. Are we truly alone in the cosmos? This question has fascinated and inspired humanity for centuries, stirring our imagination and driving scientific curiosity. Today, thanks to incredible advances in technology and space exploration, we stand on the brink of potentially answering this age-old question. At the heart of this new era is a revolutionary observatory, the James Webb Space Telescope, or JWST. This telescope, positioned more than 1 million miles away from Earth, is designed to peer deeper into the universe than any previous instrument, capturing light that has traveled across time and space for billions of years. One of JWST's recent and most intriguing discoveries is an exoplanet orbiting a distant star approximately 120 light-years from Earth. This planet, known as K2-12B, resides in the constellation Leo. At first glance, K2-12B might seem like just another point of light in a vast sea of stars. However, as scientists turned their powerful instruments towards it, they uncovered a world unlike any we have seen before, one that challenges our understanding of planets and habitability. K2-12B belongs to a rare and fascinating category called sub-Neptunes. These planets are larger than Earth but smaller than Neptune, and they don't exist in our own solar system, which makes them difficult to compare with familiar worlds. Sub-Neptunes are often described as in-between worlds. They are not quite the rocky planets like Earth, nor are they full gas giants like Jupiter or Neptune. Instead, they possess characteristics that lie somewhere in between, wrapped in thick atmospheres and possibly harboring vast oceans beneath their clouds. What makes K2-12B especially exciting is its orbit around a cool, dim red dwarf star named K2-18. This star is much smaller and less luminous than our Sun, and K2-18b orbits it closely, only about 0.18 astronomical units away, which is much closer than Earth's orbit around the Sun. Despite this proximity, the cooler nature of red dwarfs means that K2-18b lies within the habitable zone, the region where conditions might be just right for liquid water to exist, a crucial ingredient for life as we know it. Using JWST's sophisticated instruments, scientists detected water vapor in the atmosphere of K2-18b, a breakthrough discovery that suggests the potential for habitable environments far beyond our solar system. But the revelations didn't stop there. Additional data revealed the presence of methane and carbon dioxide, gases often found in planetary atmospheres and potentially linked to biological or geological processes. The most thrilling discovery, however, was the tentative detection of a molecule called dimethyl sulfide, or DMS. On Earth, DMS is almost exclusively produced by marine microorganisms living in the oceans, and it plays a vital role in cloud formation and climate regulation. The presence of DMS on K2-18b, if confirmed, could be the strongest evidence yet of life beyond Earth. A chemical signature that whispers across the vastness of space, hinting at biological activity on a distant world. Although this discovery is preliminary and still under careful review, it places K2-18b at the forefront of the search for extraterrestrial life. While it may not be home to lush forests or intelligent civilizations, K2-18b challenges our traditional ideas about where and how life can exist, opening our minds to the possibility that life might thrive in environment, high-end worlds and the future of exoplanet exploration. To fully appreciate the significance of K2-18b, it's important to explore a new concept in planetary science. The high-end planet. Coined by astronomer Niku Madushan in 2021, the term high-end blends hydrogen and ocean to describe a class of planets rich in water, enveloped by thick, hydrogen-rich atmospheres. High-end worlds are unlike anything in our solar system. They can be up to 10 times the mass of Earth and feature vast global oceans hidden beneath dense layers of clouds and gas. Unlike massive gas giants such as Jupiter, high-end planets may sustain liquid water oceans under their thick atmospheres, heated internally or by the star's radiation trapped by their atmospheric layers. Even though surface temperatures on these planets might soar above 200 degrees Celsius, 392 degrees Fahrenheit, their deep oceans could be protected from extreme heat and pressure by layers of gas and clouds above them. On Earth, certain extremophiles, organisms adapted to survive in the most extreme environments, thrive in places like deep-sea hydrothermal vents and acidic lakes, offering tantalizing analogues for life that might exist in such harsh conditions elsewhere. K2-12B may well be an example of a Hycean world, and this possibility radically expands our understanding of where life might exist in the universe. It encourages us to think beyond Earth-like conditions and consider a broader spectrum of habitable environments. But how exactly did JWST detect these atmospheric molecules from such a staggering distance? The answer lies in the clever use of transit spectroscopy. When K2-12B passes directly between its host star and Earth, a small fraction of the star's light filters through the planet's atmosphere. Different molecules absorb light at specific wavelengths, imprinting unique fingerprints on the starlight. JWST captures this light and analyzes it to determine the chemical composition of the atmosphere, revealing clues about the planet's environment. In just 5 hours over 2 observation sessions, JWST detected water vapor, methane, carbon dioxide, and the potential biosignature dimethyl sulfide. This incredible achievement highlights the extraordinary capabilities of JWST and sets the stage for a new era of atmospheric characterization in exoplanet research. However, the detection of DMS remains tentative and demands further observations to confirm. Future observations by JWST and upcoming space telescopes, such as the European Space Agency's Ariel mission or NASA's Habitable Worlds Observatory, will build upon this foundation. These missions aim to explore exoplanet atmospheres in greater detail, helping us to distinguish biological signatures from non-biological ones with greater confidence. Patience and time are key. Repeated observations of K2-12B and similar worlds, combined with refined atmospheric models, will deepen our understanding. This expanding knowledge challenges the old paradigm that only Earth-like planets orbiting Sun-like stars can harbor life. Instead, we are discovering that life might flourish under a wider variety of conditions than ever imagined. If high-end planets like K2-12B are common throughout our galaxy, habitable worlds may be far more numerous than previously thought, potentially increasing the odds of finding life beyond Earth by orders of magnitude. This paradigm shift invites us to embrace a universe that may be teeming with life in forms and places beyond our current comprehension. Ultimately, K2-12B stands as a powerful symbol of possibility. It reminds us that we are only beginning to scratch the surface of the universe's wonders. Whether we eventually discover simple microbes or advanced civilizations, each step forward brings us closer to answering one of humanity's most profound questions. Are we alone? So keep looking up with curiosity and wonder, because the cosmos isn't finished surprising us yet. Somewhere, orbiting a quiet red dwarf star, a distant sub-Neptune world waits, ready to share its story and, perhaps, to